So in this video, we will look at the electrical field E near a charged wire, an electrically charged wire, okay, that has a linear charge density of lambda equals the charge of the wire divided by the length. Now we want to find the electric field at a distance r from this wire. Okay. So one of the things we'll assume is that this length r, the distance r from the wire, is much less than the length of the wire. So for practical purposes, we can treat the wire to be infinite in comparison to the distance of the point from the wire. Okay, so let us assume that we have a small segment of length dx on one side. So the contribution of the electric field, okay, from that particular segment at this point will be a vector in this direction. So by symmetry, we can always find another segment located on the other side, okay, at a distance of minus x, okay, from the center, okay, where the electric field contribution looks like this. Okay, now at this particular point, so what happens here is that since this point is equidistant from these two, this point is equidistant from these two segments, the electric field vectors are equal in magnitude. Okay, but if you look at the magnitude of the y component, these will be equal and opposite. So the net component, okay, of the electric field in a direction parallel to the wire is actually 0. So which leaves us with electric field component that is in the radial direction. Okay, so that's the important part. So if you look at the electric field has this formula. So 1 over 4 pi epsilon 0. Okay, so and here is the q, okay, divided by r square. Okay, r here r square is by the Pythagoras theorem square x square plus r squared. So we have x square plus r square, and then we want to find the x component of that, so we multiply this by cosine of theta. The cosine of theta is nothing but r divided by x square plus r square square root. Now since q here is nothing but the lambda times dx, right? So we are looking at the contribution of this particular component, okay, to the electric field here. So the charge here is just lambda times dx, the linear charge density times the length of that wire. Okay, so and that is the small contribution to the electric field, okay, along the radial direction. So that's the important thing. So if we want to find the electric field, okay, the total electric field, we will have to integrate, okay, 1 divided by 4 pi epsilon 0 r divided by x square plus r square dx divided by square root of x square plus r square, okay, times lambda, and we integrate over the length of the wire. The length of the wire goes from minus infinity to infinity, okay, from minus infinity to infinity. So here this is valid as long as r is much less than the length of the wire, okay, as I said before. Now to facilitate this integration, let's make this transformation. Write x here as r times tan of theta. Okay, so dx here equals r times secant square theta d theta. Okay, so that's what we get. So So E here becomes 1 divided by 4 pi epsilon 0. And so when x goes to infinity, theta goes to pi over 2, x goes to negative infinity, theta goes to negative pi over 2. So we have the limits as being negative pi over 2 and pi over 2. So there is r times lambda divided by r square times 1 plus tan square theta, okay, d theta secant square theta divided by r times 1 plus tan square theta in the square root. So what we observe here is that the r's here cancel out. Okay, the r's here cancel out. Okay, so okay, so let's just continue. Okay, actually there is one thing that I did miss. So there is an r here that should be in there. Okay, so r. So we know that 1 plus tan square theta equals secant square theta, right? So we know that. So and the square root of that is square root of that equals secant square theta. So what we can do is we can write this as 1 divided by 4 pi epsilon 0. One of the r's gets cancelled out here. There is lambda, okay, by secant square theta times secant square theta divided by secant theta d theta and divided by r, and since r is a constant here, we can take it out of the integral sign. We go from minus pi over 2 to pi over 2. So we very easily we see that secant square theta cancels out and 1 over secant theta is cosine of theta. So we can write this as lambda divided by 4 pi epsilon 0 r minus pi over 2 to pi over 2 cosine theta d theta. Okay, and that is nothing but lambda divided by 4 pi epsilon 0 r sine of theta. Okay, because the integral of cosine theta is sine of theta from minus pi over 2 to pi over 2. So it's lambda divided by 4 pi epsilon 0. Okay, and 1 minus of minus 1. So that becomes 2 lambda divided by 4, and there is an r that goes in there, 4 pi epsilon 0 r. So one of the 2's get cancelled out. So we get the expression lambda divided by 2 pi epsilon 0 times r. Okay, so that's the electric field in the radial direction, which is which we found with a lot of effort by solving this relatively complex integral. Now, however, the thing to do is to use Gauss's law to greatly simplify this computation. And so what we do here is we create a Gaussian surface which looks like a cylinder, okay, and it is symmetrically placed about this wire. So now here is that the statement of Gauss's law is epsilon 0, the surface integral of E dot ds, okay, is the enclosed charge. Is the enclosed charge. So if this has a length L, then the Q here is nothing but lambda times L, where lambda is the linear charge density. Okay. So now we know that the electric field is radial in nature. So the integral essentially is the integral over the curved surface, right? If you consider the integral over the flat surfaces, the electric field is radial, but the normal to the surface is along the wire. So the electric field and the surface normal are perpendicular to each other, so the contribution from the ends of the cylinder are actually zero. So if you see that, okay, now, so this surface integral essentially becomes epsilon 0 times E times the surface area of the curved surface is 2 pi r times L, right, equals lambda times L, right? So the L's cancel out, so we get E equals lambda divided by 2 pi epsilon 0 r. Okay, so look at this relatively easily obtained result, and look at this same result that we obtained in a much more complex way, right? So this indicates that the power of Gauss's law, right? So we don't need to do this relatively complex integrations, the complex mathematics, okay, in order to to get the same answer. So in the first approach, we started with Coulomb's law, okay. We found the components, uh, you know, in a direction that was perpendicular to the wire, and that is in the radial direction and along the wire, and we determined that the components along the wire actually cancelled out, right? And as a result, we integrated over the wire, assuming that the wire is infinitely long compared to the distance of the point from the wire, and we got this answer. So using the same symmetry ideas, we use this Gauss's law, which is a much more compact way of representing the solution, and we found the solution much more easily. So this should motivate all of us to use Gauss's law more often, okay, in situations that permit us to exploit the symmetry of the problem. Thank you.